Okay, all right, so time to start. So our next speaker is Chris Rackauckas from MIT Mathematics, and so he's going to talk about generalized physics-informed learning through language-wide differential programming. So this is going to be, so we have a little bit of a sequence, so to speak, that has more of a focus on software. So first off will be by Rackauckas, and then we're going to have Lulu at 11, who's going to talk also about software aspects with Deep XD. So Christopher, yeah, thank you very much, Chris. Thank you very much for giving this presentation, and thanks. So the floor is yours now.
All right, thank you very much. Yeah, so I'm Chris Rackauckas from MIT Mathematics. I also have a joint affiliation with the University of Maryland School of Pharmacy. And I'll be working that into this talk because there's some very relevant things going on in the world with pharmacology right now. So, so just to start, the way that I like to describe a neural network is really that it's just a nonlinear function approximation, right? So if you wanted to approximate e to the x, right, you would know how to do that as a polynomial, right? Because Taylor's theorem tells you what a1, a2, a3 would be. They're just defined by derivatives. If you wanted to do a nonlinear approximation, because you have a nonlinear function, maybe you can write down a form that works for your function, find the right coefficients, and in some cases, you can know some very specific information to do this well. And for a general nonlinear function, though, can you do something similar? And that something similar is a neural network. So a neural network is really just this thing where you put it in, you do a matrix multiplication, you add a vector, you do some nonlinear functions, so that's tanh, ReLU, etc. You then do another matrix multiplication, add a vector, nonlinear. You just repeat this process for layers many times. And it turns out that that is a way to be able to approximate pretty much any function, right? So any sufficiently nice function can be approximated by a large enough neural network. So it is just something that does a function approximation. And so we're thinking about this then as what we call a universal approximator, something that can approximate any possible function. So other things that can work as stand-ins instead of a neural network are Fourier and Chebyshev series, tensor product spaces between polynomials and Fourier series, radial basis functions. All these things are doing the same similar thing. So why do we look at neural networks here? Well, it's because neural networks are universal approximators that work well in high dimensions. And there's some very recent theory that basically says that the number of terms that you need in your neural network as you go to very high dimensional spaces grows polynomially with the amount of dimensions. So if you're to use tensor product spaces, the number of terms that you have to take for very high dimensional spaces is exponential instead of polynomial. So that's what we call overcoming the curse of dimensionality. Now, but for a lot of what I'll be talking about, you can replace neural networks with any of these other universal approximators. It really just is a way of turning a function problem, a problem of finding a function, into a problem of finding a finite number of parameters, right? And so physics-informed neural networks are one way of utilizing a universal function approximator within the context of a differential equation modeling. So in this case, you would have a neural network that approximates your your solution to the differential equation, right? So x and t go in, and now you have u of xt. And then you would ask questions like, well, if u is actually the solution to this partial differential equation, then it should satisfy, linear operator applied to u should be equal some function, right? So that's the way you'd write down any of these partial differential equations. And now since you have a neural network framework with you, you can take derivatives, so the derivative with respect to t or x, and you can define your partial differential equation in terms of terms that come from your universal approximator, and you will know whether your parameters for your universal approximator are correct because the cost function will be 0, right? So the cost function is 0 when it exactly satisfies that PDE, and so that becomes your training process. Find the right parameters for my universal approximator such that this loss function approaches 0. And so this has been demonstrated to perform a lot of wonders because you're utilizing your prior scientific knowledge to increase the data efficiency. And one of the really nice things about physics-informed neural networks is that it can utilize the deep learning framework, right? Because you just have a big neural network, you take derivatives of the neural network. That's what these frameworks were for, right? Taking derivatives. And so there's not much else that you need to do. And so the science behind physics-informed neural networks has been, how can I use these to effectively solve scientific problems in a way that's better than just a pure neural network, right? But the question I've been looking into is, can we dig deeper into the scientific simulators to utilize more of the structural knowledge that exists there? So what do I mean by this question? Just want to make sure that everyone can hear me right?
Yeah, no problem. Yeah,
Yeah.
it's great. Yeah, we can hear you.
Yeah, just got no feedback, so it's kind of scary. So yeah,
Well, yeah, no, it's all very silent, but we can hear you.
Yeah, so can we dig deeper and utilize more of the structural knowledge? And what do I mean by this? Well, so when we go from, so what I want to do is I want to go from pins to augmented modeling. So these pins, what they're really doing is they're putting a neural network around the model. They're basically saying, what we want this neural network to learn is the entirety of our partial differential equation. And then if we have, our PDEs, some linear terms, then we can take derivatives of it and be able to reconstruct that in our cost function. And so the pros of this is that the loss function has only neural networks, and so backpropagation works right out of the box. And you can use this to solve lots of interesting problems. So, Rossi just described how you can use this to accelerate the solving of inverse problems, for example. But there are a few difficulties that come out, right? Because if I take this trained neural network and I want to ask what its parameters mean, the parameters don't necessarily have much meaning, right? You can redefine your problem such that your neural network fits in smaller pieces to be able to have some parameters that have meaning. But generally, that neural network itself is kind of this amorphous blob that just happens to have captured enough physical information in terms of its loss function, right? So one of the things one of the problems that shows up in this case is that you cannot use optimized scientific simulation software, right? So people have spent, 10, 20 years writing optimized differential equation solvers. And if you want to say, well, let's use an adaptive fifth order BDF method, for discretizing this in time, you can't necessarily just take that existing software and throw that into TensorFlow and then backpropagate through it, right? You can't not necessarily just take an existing climate model and then just stick neural networks over it. You need to do something a lot more involved in those kinds of cases. And one of the other things that really seems to be showing up more is that it might be a little bit unstable to train because manifold constraints are only true when the loss is satisfied. So a lot of times what you see in these physical models is that the solution lives on a very low dimensional manifold, right? And when the loss is truly satisfied, right, when the loss is zero, then your solution will live on that manifold. But before that's the case, you don't necessarily have the manifold constraints. So for example, imposing something like conservation of energy, that will only be true when you can put that inside of your loss function, but only after you've changed the parameters around will conservation of energy hold. And the difficulty there is that you might require conservation of energy for your solution to not blow up over time. And so this is where you might get a lot of these, some of these stiffness issues that Paris has been talking about because of these properties of, the scientific simulators, like this, or the scientific solution needs to live on a manifold. And so what a lot of past numerical analysis has been doing has been trying to find ways to be able to reparameterize our equations to live on the manifold, so that way your symplectic integrator always keeps angular momentum and stuff like that. So can we make use of these existing tools that we have to be able to keep these manifold constraints true by design? And so this is where I get to this generalization of, instead of trying to put neural networks around our models, can we selectively put neural networks within scientific simulators? So if there was a piece of a scientific...
Just a quick comment. So, I mean, you're using the word model, but what I think you mean is the numerical solver rather, because spin makes use of the model, right? The mathematical model might be your Navier-Stokes or, climate PDE or whatever, but you mean your numerical solver is the part.
Yeah, well, I mean, so whatever simulation software you have that goes along with the model. Yeah.
Right. Yeah.
So for example, if you do have one of these, global climate models, there might be a portion of the model that you know less. And this might be what you're trying to target with your physics-informed neural network. And so the question might be, well, what about replacing that, there's a block of code inside of your climate model. Can you just replace that little block of code with the neural network and directly train that small piece of it? the nice thing is that everything that you have with your climate model, the thing, you have developed all these, discrete Galerkin methods that are optimized and stable for these kinds of equations. All of that knowledge would then carry over to this case. You can use the fast forward methods, that kind of gets around one of these difficulties with physics informed methods. But the real difficulty is that you cannot just necessarily throw a neural network into an arbitrary scientific simulator, because now you have the problem of how do I backpropagate through the rest of this simulation code such that I can optimize this neural network within this context, right? So what I want to really do is show two things, right? Show that there is a way to be able to train neural networks directly within the context of scientific simulators, but then also B, show why you might want to do this. So I'm going to show that you can do automatic discovery of equations, accelerating scientific models, and deriving these neural transformations to solve very difficult equations by utilizing neural networks in very small portions, or very small parts of a model. So what I need to first describe is why we're using Julia here. So the reason why a lot of people come to Julia is because it's a high-level language that is expressive. So you can take your mathematical function, described on the left there, and you can write it into Julia, use the same Unicode and all that, and you have a simulation. But that's not the reason to use Julia. The reason to use Julia is because it's fast. So just because you wrote in a high-level language doesn't mean it has to be slow. In something like R or Python, when you do write your entire program inside the higher level language, then you end up having these speed issues because the interpreter gets in the way. And so generally packages in R and Python are actually written in C++, right? With Julia, you have a form of JIT compilation on a automatic optimizing type system that is actually kind of defining the C code along the way for the types of your whole problem, and then is generating an optimized code. And the reason why that's interesting or useful here is because it means that people who are building packages in Julia actually are writing almost the whole package in Julia. So if you look at how PyTorch is generated, it's only about a third in Python. TensorFlow is about half in Python, whereas in Julia, the flux.jl library is 100% Python. And the interesting thing here is that what we can realize is that if all or most of our packages are pure Julia code, you don't need to target a ML sub-framework, so some sub-language to do automatic differentiation on to be able to generate code and be able to work with. What you can do is you can target the actual Julia AST itself, and then arbitrary Julia packages will be compatible with whatever you're calling machine learning. All right, so there is no sub-language like in TensorFlow. There is no torch.numpy, which is different from numpy, right? And with the Julia, you can actually just say, I'm going to differentiate the Julia code itself and give you new Julia code. And then with that, then anyone who has written a package in pure Julia is automatically compatible with your differentiation system. And so one of the core components of this is the Zygote differentiation library, which is using a source code transformation for mixed mode AD. So by mixed mode, I mean you can use forward mode as of a few weeks ago, and then but it's also has its core has always been reverse mode automatic differentiation. And what it's doing there is it's doing the source code transformation of a Julia code to another Julia code. And the reason why it's able to do this, even though it's a dynamic programming language, is because the Julia compiler is, when it's performing the JIT compilation, it is finding the full context of the code that is all going to be satisfied, right, in order to perform the JIT compilation. And then you can hook your own compiler passes in right before its JIT stage. And then at that stage, all of the, the entire function that's going to be used, all of the types because it's done a full type computation. And at that point, you can use that to be able to hijack its JIT compilation and have it build a different pass or a different function, which computes both the solution and something that will give you this derivative. And so in some sense, this is almost like taking a Julia code and automatically putting it onto TensorFlow. Like you get the computation graph and then working directly on that computation graph. And so the interesting thing here is that it works on general Julia packages, right? So no one needs to opt in. No one needs to use torch.numpy. No one needs to use jax.numpy, right? There's nothing that needs to be done to a package such that you can do this with. And so therefore you can take existing scientific libraries that utilize, define user-defined types, have their own modules, use multiple dispatching, They can use all these language constructs and it doesn't matter. You can still stick that package into your differentiation workflow. And the other interesting thing that comes out of this is because since we're targeting the Julia AST itself, other things that are targeting the Julia AST are directly compatible. So there's for diff.jl, which is using a forward mode with automatic SinD on small scale operations. There's other reverse mode packages. There's a reversible AD package. So instead of having to store values of the forward pass to do reverse mode, you can have some programs where you know how to do the reversible interaction, and you can then define a backpass on that. So there's all these other different tools that we can make use of. And if everything is all targeting and building the same kind of code, you can actually just compose all them together. So you can use Zygote over a reverse diff, over a forward diff, and that is a way to be able to get a third derivative with two reverse modes, one forward mode, using 3 different packages or 3 different methods for the automatic differentiation, where they're all optimized in different ways. And so the interesting thing here is that the machine learning stack that we've built up over these years is pluggable and extensible, right? There's nothing that you can really point to as the true source of the machine learning stack. What you have is you have one library, Flux, which defines standard machine learning architectures in just Julia code. So if you open up the package and you just look at it and you know Julia, you can see how every little detail of like a recurrent neural network and LSTM is defined. And then there are packages which add GPU support to arbitrary Julia code, and then things that add differentiation to arbitrary Julia code, and that is what we call our machine learning stack. But what that means is that there's no core that you have to try to modify. There's no TensorFlow compiler or actually XLA that you have to modify to make this thing work. You can plug any new pieces, any new packages in, and call this as part of your machine learning. And so what I wanted to show is how can you use this differentiable programming ecosystem to enhance scientific models? And so what we can start with is we can take this differential equation solver library, right? So it has MPI and GPU capabilities. It has implicit methods with IMAX symplectic integrators, exponential integrators, adaptive high order stochastic differential equation solvers, delay differential equations. It has this whole set of features that we would never want to rewrite, right? Can we just take this and utilize this as part of what we're doing our backpropagation with? So one application of this is neural control of an implicitly defined physical system. So in this case, we define an ODE, which we solve with differential equations.jl. We use its continuous interpolation that the library provides in order to do a root finding condition. So we have to know when the ball is going to end when the ball hits the ground in order to end the simulation. That can be done through a event handling. So you need to find where y equals 0. And for that, we use a false position method from roost.jl. And so what we have to do as our simulation is we solve the ODE with this ODE solver, and then every single step we're putting this through roost.jl to be able to find if we hit a 0, right? And then backpropagation, it backpropagates through the false position method, backpropagates through the ODE solver, and then it's able to train whatever parameters you want in there. So what we can do is we can have a neural network that takes in the wind and the wind velocity and the target length, and what we can output from that is what angle and you should be aiming the trebuchet with and what weight you should be putting in there. And then together, this neural network can be trained to be able to satisfy this control problem. So this is one case of putting a neural network on top of an ODE solver, which is also using a root finding code. But now what we can do is we can say, well, if we can just compose everything at will like this, there are probably more interesting problems or questions we can start to ask with these kinds of tools.
So I just have a quick question. So the neural network here, what is it representing? Because you know the physics equation is here.
Yeah, so it's representing the solution to the inverse problem, right? The inverse problem is if I was to know the wind and the target velocity, how should I be aiming my trebuchet? So what angle and weight should I have such that I would hit the target, right? So in some sense, this is an inverse problem that you can write down, and you can say, if I had this wind and target, I would then choose this angle and weight. I would send it through the ODE solver. I'd run the implicit thing and tell me where it landed, and then my cost is how far I am from the true target. And now you can take that itself is a nonlinear function, right? And so then you can have the neural network be that nonlinear function, and you can train it to have the weights that to satisfy that R2 to R2 function. Right, and so so instead of just solving inverse problems now, what we can start to look at is, can we replace parts of an ODE with neural networks to learn missing parts of physics or missing parts of other models? So one case of this is the neural ordinary differential equation, where you can say U prime equals a neural network, right? And Rossi also described a case of this in his last talk. But the next thing that you can say is, well, what if I have U prime equals a known differential equation, but also with some neural network terms in there for accounting for some hidden information? And can I find what the missing parts of the model are? And this is what we call the universal ordinary differential equation. So this augmentation between differential equations.jl with the so differential equations.jl mixed with flux.jl mixed with zygote.jl, and this conglomeration has kind of become what we call this diffeq-flux.jl, which is something that can train universal ODEs, universal SDs, all these different types of differential equations using the high order optimized implicit methods of the differential equation solvers. So to really showcase what this kind of library can do, what I wanted to explore was an augmented scientific workflow to try to figure out what the right model would be for a COVID-19 outbreak model. So we can take a model, so someone had made this conceptual model that is fitted against the real data from the Wuhan region on the outbreak. And one of the difficulties that you see here when coming up with these biological models is that you can have these terms here. Beta of t is a very complex term which has a power to the 0.11, and coming up with these models is a difficult process. So the question that we wanted to ask was, could we automatically, from a small amount of data, recreate this model, and from that small amount of data, then be able to have accurate extrapolation properties, right? So the first thing that you might want to do is just say, well, if I have data and I'm trying to find a dynamical system, let me approximate the whole dynamical system with the neural network, right? This is the first approach we might take.
So can I ask the beta of t? What does that represent?
It represents the exposure, yeah. Sorry, that was an important point. So beta of t represents the exposure. The exposure model can be different for different countries, depending on how much quarantine there is and how much people are actually listening to the quarantine, right? So the actual exposure model is something that is very country specific, and we want to be able to figure out how to do this automatically, so that way we can then train on data to automatically pull out how exposure is different between different countries, and understand how the quarantine policies are, or whether they're effective or not. So this is something that someone specifically went in and hand optimized this to the Wuhan region, but we want to see if we can automatically do this with the machine learning-like approach. So,
but the problem is this model is a bit weird, because it's completely it's just a model in time. There is no spatial component, so I don't even get it. I mean,
well, right now we're looking at, yeah, right now we're, oh yeah.
Sorry, there's no concept of contagion between different towns and so on.
Yeah, this is not a spatial model. It's just a time model right now. Yeah, so it's really just trying to see what the effects of the quarantine are through one exposure term, which means that, yeah, the exposure term is an empirical term. You can find it per country or you can find it per town, but it is something that is really hard to find the correct term for.
So basically you're assuming it's sort of a place that has been completely isolated, has no contact with the outside, and then you're looking at different strategies to contain the virus inside that place.
Yeah. And so one thing that you can do is you can say, if we have this data, we can try to recover the dynamical system just by saying U prime equals the neural network that defines the dynamics. You can throw that into the differential equation solver, and what you can do, and what it will do is it will fit the dynamics for the 3 weeks of data that we had it on. So here, the black line showcases where we stopped having the data, and it fits fine in where we have data, but it doesn't seem to extrapolate quite well. And the reason is because, in this case, we used some information about how differential equations work by having it be inside of differential equation solver, but we haven't used all the information that we have. So the next thing that you can do is you can say, well, there's a lot of information that we have about the recovery of the disease, right? So there is a fixed recovery rate that we tend to know that is kind of independent from the exposure. And so if we can use a lot of the SEIR model directly with these already known coefficients, the thing that we actually don't have a good feel for is what the actual exposure rate is, right? So if you know that people have the disease, what is the rate at which they actually infect others? So what we can do is we can replace that term of we can say that we can assume that we know most of the SEIR model, but say that we don't know this one term, and we can fit that term to the data by using this universal differential equation approach. So we solve the full differential equation with a neural network. We backpropagate through the differential equation solver that tells us how to change our parameters until we iteratively fit the parameters. And what we see is that's able to extrapolate a lot better, right? So even with just 21 days worth of data, we can extrapolate out to about 40 days and get accurate predictions on how many people are going to be exposed. But it's still not that great, right? So the next thing that we want to look at is, so you can do this methodology called the sparse identification of dynamical systems, where what you do is you build up a matrix of observables from your data, and then you perform a linear regression in order to find out what the coefficients are in a observable basis that will define your differential equation. And in a lot of cases, this can work if you have a lot of data. But here on the right, I'm showing what happens if you perform SinDy directly on the dynamical system with a large dictionary, and you don't necessarily pull out the correct equations, or you don't necessarily pull out even very simple equations, right? And so, and this doesn't extrapolate very well. But in this case, we have a dynamical system where we know most of the model. And what we can do is we can say this one unknown term that we have, we can perform a sparse regression of that unknown term. And now we have an augmented SEIR model. Maybe that is a good model for performing this extrapolation. And what we can see is that if we perform this process of finding the observables for the unknown portion and then reparameterizing this unknown portion into a sparse basis, it basically says that a good approximating term here is for the 21 days is something that's linear in terms of just two of the variables. And then when you actually replace that into the equation, so now we found a new set of SEIR model, or new SEIR model that fits for 21 days, this sparse identified form of the universal ODE is then able to extrapolate pretty well for at least 60 days. So this is what the workflow looks like, right? So we're using a neural network to approximate unknown parts of models, and then we're using sparse identification to be able to then bring this back to equations, and then we can actually have the computer program spit out what the LaTeX for the model should be. And so,
can you explain a little bit can you explain a little bit the U1, U2?
Yes, so U1 and U2, these are the variables of the model. So these are actually S and I believe in this case. So yeah, and so so the computer program itself has another step where it actually spits out the LaTeX as the output, but I'm just kind of showing there that when in terms of this identification, right, what it's really doing is it's finding the coefficients in a basis. So it's basically putting together this dictionary. These are all the terms that you could have, and then finding a linear combination of the terms in your basis. So here we use the basis of trigonometric functions and polynomial functions, and you have the coefficients there. This is what it pulls out in this case, where it's only learning the specific terms that were missing from the model. It basically just says the missing term that you first approximated by a neural network, you can then get rid of that neural network and replace it by just this term that's linear in S and term that's linear in I.
But you no longer have a function of time in there?
It does not necessarily have a function of time. Yeah. So you will not necessarily always pull out the correct basis, but what you'll at least find is you'll find a sparse basis that has at least better extrapolation properties. In order to find the correct basis,
time was in the time was one of the variables you could consider.
Not in terms of this study right here. Yeah. So you could have time in terms of you could have time in this basis and then look for that function itself. This one, it would be the true model actually has a rational function to the 0.11 power. And so you generally won't know that's going to be in your basis. So we didn't want to bias it by getting too close. But what we showed is that if we took a very naive basis, right, our naive basis is just polynomials of things of SEIR and trigonometric functions. What we could do is we could still pull out a sparsified model that is able to get that is able to extrapolate beyond its training data in an accurate fashion, right? How far will that go? We would need to do a lot more study on this. But this is at least what we have going for current studies with the School of Pharmacy. This is hot off the press as of last weekend.
Yeah, the problem is that this seems to have little to do with the reality on the ground. I mean, things do change quite a bit as a function of time. The methods to, detect who's infected. I mean, there's a lot of things that seem to be missing from this
giving a
model.
very simplified model to show this in 2 minutes.
Right, yeah.
So essentially that is the ML augmented workflow, just kind of in a nutshell, right? So we can identify unknown parts of a model. So we can use the model that we have, and we can build this universal ODE where we replace terms that we didn't know with a neural network. We can train the neural network to capture the missing mechanisms, and then we can sparse identify the missing terms to be mechanistic terms, and then we can utilize our scientific knowledge to understand what those identified terms mean and whether they're scientifically plausible, and then we can use that to be able to extrapolate, right? And we can make sure that it has correct asymptotic properties and it has a much nicer basis form. It tends to extrapolate a lot better than using the pure neural network approach. And so there are other cases that we've looked at with this. So for example, in an ecological model, we took the Lockable-Volterra equations, and we said if we only knew that the amount of prey grew exponentially and the amount of predators decreased exponentially, could we recover the missing interactions between the predator and prey? And a very similar process of training the neural networks embedded within the differential equations and then doing a sparse basis regression. In this case, it's actually able to directly pull out the correct terms, so it actually gives you directly the quadratic terms back. And then when you extrapolate, even though the training data was from 0 to 3, where if you look at that, it only sees like an exponential decay and an exponential growth. It's able to predict that in the future you're going to have a cyclic relationship, right? So the points, the circles are the training data, but when we extrapolate it beyond that, the line, which is what we predict is going to be the future, actually matches up with the future of the Lockable-Volterra model, right? So essentially, what we're showing here is that by using this approach, we can augment the way that we're finding models with a neural network and composing that with these sparse identification processes. And so what we've done over the last year is we made sure that this connection is compatible all the way throughout the differential equation solver ecosystem. So that way, if you wanted to do this on large nonlinear partial differential equations, you can. So this example is 15 lines of code of showcasing that you can make a neural differential equation with batching on the GPU, with high order adaptive implicit ODE solvers, with matrix-free Newton-Krylov and preconditioned GMRes using checkpoint and adjoints, right? You can slap all those together, and if you had a very difficult equation, these are the kinds of methods you need to use to solve it effectively. This library has these tools in order to do that. And so if you want to look at how to do the automated sparsity detection, preconditioned Jacobian-free Newton-Krylov, all these kinds of tools, you can take a look at the tutorials. But next I want to show one of these other use cases of utilizing neural networks within differential equation solver frameworks. So on the left, I show a convolution operation from a convolutional neural network. And all that a convolution operation is it's a stencil, right? You have it set, when it's centered around a given point, you use, here for example, use one from the top left, one from the top right, one from the bottom left, one from the bottom right, and the middle point, right? And so your convolution operation is a stencil operation, which is adding the points around it. But if you actually look at the way that PDE discretizations work, they are themselves a convolutional stencil, right? So when you do finite difference method for the second derivative operator, what you get is you get a very specific stencil, 0, 1, 0, 1 minus 4, 1, 0, 1, 0. And basically what that says is that there's a relationship between, if you were to learn the stencil, then that tells you what must be happening in the governing process. So one way that we made use of that was for automatic discovery of PDEs from data. So you can say, here the truth equations are the Fisher-KPP equations. And what we can do is we can define a neural network and a convolutional neural network inside of this PDE so inside of this discretized version of the PDE. And what we do is we then train the weights of the neural network and the convolutional neural network simultaneously. And what the convolutional neural network learns to do is it learns that the weights need to sum to 0, right, which has to be true for any PDE operator. They have to be conservative. And the other thing that it learns is that the weight of the left and divided by the weight from the right minus 1, so it has to be equal to 0, which is another way of saying that the weight on the left equals the weight from the right, right? So that means that in the stencil that we have learned, the amount that's going to the left equals the amount going to the right, which is consistent, and everything sums to 0, which is consistent only with the discretization of the diffusion operator, right? So we can, once we've trained this equation, then we can actually look at these coefficients and interpret that the only thing that could have been generating this spatial process was something with diffusion. And we actually take a look at what the reaction term was. You can see on the bottom right there that the neural network learns to be a quadratic function in terms of rho, right, at every single point in space, which basically just says that the reaction term that was missing was something that's quadratic. I mean, you can use the SINDI approach on this neural network to then recover that the full partial differential equation was a diffusion equation with a nonlinear quadratic reaction. And so those are using neural networks embedded within scientific simulators to discover equations. But the other thing that we can do is we can use it to accelerate simulators. So in this case, we had the Navier-Stokes equations and, the Boston-esque version of the Navier-Stokes equations. And what people generally do in terms of these climate models is you find an approximating one-dimensional PDE for the three-dimensional PDE by taking an integral with respect to x, y, right? And the difficulty there is that you have to end up with you do not end up with a closed set of equations. You just cannot represent the 3D equations with the 1D partial differential equation. And so when you do try to represent it as a diffusion advection equation, you have that there is an unknown function inside of that PDE, and that itself is defined by a PDE. And so you actually have an infinite cascade of one-dimensional PDEs. But what we could do is we could utilize the data that we have, then be able to train and learn what that missing function is. And now we have a one-dimensional PDE that represents solutions along the z-axis of the Navier-Stokes equations, but is then able to solve it a lot faster. In fact, the difference between solving the trained one-dimensional partial differential equation versus the 3D partial differential equation is 15,000x, but that's no surprise because, I mean, a one-dimensional partial differential equation is a lot simpler of an equation. And really what we have done here is made it so that way finding the right approximating 1D PDE is something that can be done almost automatically through this neural embedded approach. And one of the other things that we looked at was, if you wanted to solve these thousand-dimensional partial differential equations, does this also fall into the same framework of neural networks embedded within scientific simulators? So if you take this semi-linear parabolic equation, it turns out that there is a relationship between this semi-parabolic PDE and what's known as backwards stochastic differential equations, right? But the difficulty is that you might not know all of the functions inside of that backwards stochastic differential equation, but you do know when you have the correct one because you have a terminating function that will tell you when it's correct. And so what we can do is so what was previously done was you can use a recurrent neural network to be able to write down this discretized form of the BSD and be able to approximate the missing term as a neural network. But what you can do instead is if you realize that this missing term is just a neural network within a forward-backwards differential equation, then you can say, here is the forward-backwards differential equation where the missing terms are replaced by neural networks. Now now this is something that is just a stochastic differential equation problem of finding a neural network embedded within a stochastic differential equation. You can then utilize high-order methods. You can utilize adaptive methods. You can utilize implicit methods that already exist in the differential equation solver library to be able to solve these equations forward, backpropagate through the solver, and train these embedded neural networks. So there are a lot of other transformations that we're looking into. So for example, a Green's function is just, if you know a Green's function, then the solution of a PDE is just a convolution of the Green's function. So can we actually directly find out how to write cost functions and be able to train to figure out representations for the Green's functions and be able to use that directly? Can we change the can we change our finite element framework such that instead of using basis that we're able to write down, we can replace our basis elements with neural networks and train them directly in context. So we backpropagate through the stiffness matrix construction, backpropagate through all the little pieces of the finite element library such that we use denser basis functions for having less elements required. These are other transformations that we're looking into in this general line of using the smallest neural networks that we can embedded within full scientific simulators. So I just wanted to end by highlighting some of this ecosystem that we've now built out that is all SciML-compatible. So the climate, so this full-scale climate model that's being built between MIT and Caltech is one of these things as a pure Julia code that is backpropagable. And so you can replace terms of that with neural networks. The robotic simulation libraries, quantum optics libraries that we've been working with, all have these portions such that you can utilize these full simulators, but be able to replace unknown parts of the physics or empirical parts of the physics with neural networks and be able to train them directly within the context of the simulator. And so for the last step here, really, we have this pharmacometric software, which is being used in live clinical trials right now. I cannot divulge all the details, but it's for a disease that is very relevant right now, where these techniques of language-wide automatic differentiation are utilized for fitting unknown parts of the models and understanding how patients are going to react differently to a drug, utilizing the data that we have from healthcare records. So in conclusion, there is a large world of opportunities I think that are out there where we can use these program transformation tricks, right? These tricks that require being able to transform one program to another, but in order to incorporate machine learning more directly within our scientific tools. So instead of using neural networks around scientific simulators, we can effectively replace small pieces of it, use smaller amounts of machine learning, and when we do so, we can decrease the amount of training that needs to be done, decrease the amount of training data that's required in order to make this more of an effective tool for large-scale simulations or things that are stiffer. And so I just want to acknowledge some people from this Julia ecosystem. And so, I mean, I have to basically say that, there are a few hundred individuals that we've collaborated with that are not in this list because building a language-wide differentiable programming ecosystem is not something that's an individual effort. It's really about building a culture of throughout everyone who's building scientific packages to make sure everything works together. So I highlighted some of the top individuals here, but there's definitely many, many more people that need to be acknowledged all throughout the Julia ecosystem. So yeah, this time I'll take questions on this whole amorphous blob of language-wide differentiable programming.
Hi, Chris. This is Lulu.
Hey, all right. Yeah, thank you very much for this. Okay, yeah, go ahead if you want to ask. Yeah, Lulu.
Yeah, I just have one question. So I think everything here can also be done in Python, like using the main key is what's the ecosystem. So as you mentioned, there are lots of libraries already developed in Julia. But from Python, I think the main thing people use Python is because of the TensorFlow and PyTorch. There are lots of techniques is already developed by these two big companies, and every single new paper they will provide the code based on TensorFlow or PyTorch. So how do we compare for the machine learning part, especially the deep learning part? So how do we compare the current ecosystem in Julia and the TensorFlow PyTorch?
Yeah, so the machine learning aspects of it are not too different, right? Because you have the same standard architectures, right? So you have recurrent neural networks, convolutional neural networks. You have, your dense layers, but you also have, transformers and all the standard GPU tools. These things are very similar, but where the difference really lies is, at least from what I know, I do not know someone who's written a full-scale global circulation model for climate directly into TensorFlow to make every little detail of that backpropagable, right? But those are things that exist. Also, things like high-order adaptive stochastic, high-order adaptive stochastic differential equation solvers. Do they exist in a way that is accessible with TensorFlow? The libraries, inside of SciPy, you use LSODA. Can you use LSODA on your TensorFlow model? Not necessarily, right? So basically, the difference here is that really these scientific tools that you're used to using inside of a scientific computing framework, These are the pieces that are now been added to be compatible with the deep learning framework, right? So generally, I don't dig too deep into most of these machine learning tools beyond, autoencoders and transformers and these kinds of details. But they exist in all frameworks, but really where the difficulty or where the difference really lies is in the tools for scientific computing mixed with them, right? So how would you use an autoencoder with the fifth order BDF method? Well, you just can't, you'd have to find a way to be able to stick the two together. And in Julia, because of this language, because of this targeting on the Julia AST, and because all these packages were built in pure Julia, these things are already automatically working.
Okay, thank you.
Hi, this is Kai. I have a question regarding this language-wide differentiable programming. The first question is that how easy is it to write the plugins for the differentiable programming that like I want to design a custom gradient?
Yeah, so there's a system known as chainrules.jl, which allows you to define your gradients in a way that it plugs into a lot of these other packages. I mean, I could just pull up the documentation here because it works on Julia's multiple dispatch rules. So if you just define a rule so here is F rule and R rule, you just have to define a function that computes the forward pass and to compute something that builds the anonymous function for the reverse pass. So if you just add these dispatches, right? So Julia is the multiple dispatch language, which sees what types you have defined in order to tell you which function to call. If you define these dispatches on R rule and F rule, these will automatically get put into the backpass of things like Zygote or forward diff2 or these other packages.
Okay, thank you. And the second question is that does the current system support like parallel computing or concurrency or things like that?
Yeah, so you can use multi-threading, you can use distributed programming, and you can use GPUs, right? GPUs can target Intel GPUs, they can target AMD GPUs, and they can target NVIDIA GPUs.
Okay, so does it require a special implementation, or it just works if you implement everything in Julia?
Yeah, so I mean, so if you just implement the full code in Julia, right, then you can use the GPU array library. So you can use one of the libraries for AMD GPUs, and you put a neural network on that, and you put differentiation on that. Then that's something that composes to be a neural network that works with AMD GPUs, right? So that you won't find like a centralized machine learning framework here, but because of the composability, those tools and each combinations do exist.
Okay, thank you.
Hi, I have a question. This is a really, really great talk. This is Nat Traskett, Sandia. So one of the really interesting things about doing PDE constraint optimization is whether you actually extract a well-posed PDE. Can you comment on what kind of tools there are in the Julia universe? Right, like, could you look at, say you wanted to extract a positive definite operator for your PDE? What kind of things are there out there? I guess this is a little bit open-ended, but is that clear?
Yeah. I mean, so you can parameterize a positive definite operator by using its Cholesky factors, right?
Yep.
So let me see if I remember that. Let me pull something up here. I'll find. I can just find the library right live here. Let's see. It is PDMaths. Yeah. So there's this PDMaths.jl library that allows you to parameterize positive definite operators. And so then you can utilize this within your differential programming framework with machine learning in order to make it so that way this operator in its learned form has to be positive definite. We know that this works with the differentiation tools because we use it inside of the pharmacometrics libraries because the operators there have to be, the Hessians have to be positive definite when we're learning covariance matrices. So yeah, this is one of the things where someone created a library for parameterizing positive definite matrices, and since it just exists in the Julia ecosystem, you can directly use this with the machine learning frameworks.
And can you comment on, are there, so there's a whole spectrum of tricks like this that you might want access to if you want to engineer some sort of guarantees into your model that you're extracting. Are there lots of things like this? Are there?
Yeah, there's lots of random tools around, right? We've been trying to capture them in diffq flux and basically be like, what are the different ways we can make use of them? One way that we've recently been looking at for doing this in general is utilizing different formulations for the discretization. So for example, instead of writing down a ordinary differential equation, you can write down a differential algebraic equation. So for example, if you write down a ODE with a mass matrix which is singular, then you can have, for example, a constraint equation. So this ordinary differential equation is requiring that the evolution has y1 plus y2 plus y3 equals 1, right? Because the mass matrix on the left-hand side of the differential equation has a row which is all zeros. And it turns out that differential algebraic equation solvers can solve these kinds of equations. And so if we use a differential algebraic equation solver or some of these Lie group integrators, we can enforce that the solution lives on the manifold. And we can then, so as long as you have DAE solvers or Lie group integrators and Cholesky factor, if all these things are compatible with the differentiation tools, you can just start composing them all together and then enforce that these constraints hold and not have to do it within the loss functions. Yeah.
Great, thank you very much.
Okay, so yeah, we're kind of running a little bit out of time. So I had a couple of questions, but I'll just maybe just ask one, which is what are the parallel capabilities of can you comment a little bit on that? Because for example, TensorFlow has the ability to run on multi-core, multi-GPUs, to some extent on multiple nodes and so on. But in the context of, for example, large scale finite difference PDEs and running on large clusters, it's much more limited. So I was wondering what's the status in the Julia world?
Yeah, and so you could definitely, so the Julia's parallelism is compatible with these differentiation tools. So you can use multi-threading, you can use distributed, and you can do multi-GPU. And it's actually a very interesting and deep story for how you can get that, how we got that working. Basically the question is, if we're doing this language differential programming, then the these parallelism components are actually part of what we need to differentiate. And so, for example, if you write a multi-threaded code, so if you write a multi-threaded code and you have a lock in there, or you use an atomic, what is the derivative of the lock function? And it turns out that the reverse mode derivative of the loss function is equal to unlock, and the derivative of unlock is lock. So that way, when you build the backwards pass, it's actually relocking and unlocking correctly in the reverse pass. And so we've actually gone through and made sure that the concurrency tools of the Julia programming language are actually compatible with the differentiation. And so then that means if you use any of these multi-GPU, multi-node types of parallelism that is built in with the language, the differentiation tooling knows how to correctly build backwards pass code that is also multi-GPU and also multi-distributed. Yeah, that is a very interesting and deep question that we could probably be its own talk. Yeah.
Yeah, but for example, just quickly, you can if you do message passing communications, you can reverse the communication. Yeah, because you talked about the shared memory.
Mm-hmm. Yeah, so what I mentioned was with shared memory and locking, but yeah, you can use the distributed programming with this. This is one of the things that we've been demonstrating inside of this diffq-gpu.jl library with multi-GPU. So the way that we're using multi-GPU is we set it up through the distributed programming plus the GPU library. So yeah, it works with the message passing and the multiprocessing, but to exactly describe how to do that, I think I would need a lot more time. But yeah, you could dig into to find how it's done in Julia. So if you look up parallel computing in Julia, you can go to the manual page. This is the page that describes how to do multi-core distributed processing.
Right, yeah.
Right, and it's really the question is this compatible with differentiation? Yeah, it is, and you just need to make sure you use it in the correct way. Yeah.
Okay. All right, thanks.